Good morning, chemistry students. This is your Chapter 15, Day 3 notes. We're going to do all of Section 2 of Chapter 15 today. I know that maybe seems like a lot, but it's really not that much. So this section is about ionic bonds, and we've already talked about ions, so that will make that a little bit easier. So as we talk about the formation of ionic compounds, we're going to talk about the fact that an ionic compound is a compound, and here's an abbreviation for compound to save you a little bit of writing, composed of or made of cations and anions. So remember, cations are ions with a positive charge. Typically it's metal atoms that become ions and become cations. Anions are atoms with a negative charge. Typically anions are going to be made of nonmetals. Sorry about that, my son didn't know I was recording. So again, ionic compounds are a compound that is made of cations and anions. Cations are going to be metals because metals tend to lose their outer shell electrons to become positively charged, and nonmetals are going to be anions because they typically are going to gain electrons to become an ion. So although ionic compounds are composed of ions, ionic compounds are electrically neutral. So that's going to have a lot to do with the ratio in which the cations and the anions combine. They're always going to be combining so that overall the compound doesn't have a charge, so that it is electrically neutral. So another way to say that is that the total positive charge of the cations equals the total negative charge of the anions. So, what specifically is an ionic bond? Ionic bonds are defined as electrostatic forces that hold ions together in ionic compounds. So electrostatic, first off, the static part of that. Static means not moving, okay? And electro refers to like an electrical attraction. So we're talking about like an electrical attraction that occurs between things that aren't moving. Okay, and that is what holds these ions together in ionic compounds. It's called an ionic bond, but it's this attractive force. And again, hopefully it makes sense that they have an attractive force because anions and cations have opposite charges. and attract one another. By means of these electrostatic forces. So part of what makes ionic bonds so strong is that you have a positively charged cation attracted to a negatively charged anion. And as you already know, opposite charges attract, so this makes for a pretty strong bond. So for ionic compounds, we're going to take a look at an example, which is sodium chloride, table salt. Okay, so we're going to look at it with those electron dot structures. So when you look at a periodic table, sodium is in group 1A, so it only has one valence electron. Chlorine is in group 7A. It has 7 valence electrons. So what happens when this forms this bond? This one electron here, it's going to get transferred to chlorine. The result of that is I have sodium ion, and it has a full outer shell. It's gotten the electron configuration of neon, okay, but we're not showing any electrons around it because remember its third energy level is empty now. And chlorine has become chloride, and it has a -1 charge. You can also kind of look at this in terms of electron configurations. So sodium's electron configuration is 1s2, 2s2, 2p6, 3s1. Chlorine's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. Okay. Now, what happens is when chlorine gets an electron, it gets the electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. That's the same as argon. At the same time, sodium as an ion has the electron configuration of 1s2, 2s2, 2p6. Okay, it's lost that electron in its third energy level, which is the electron configuration of neon. So again, why does this compound, sodium chloride, always exist as one sodium ion bonded to one chlorine ion? That is because both elements get the stable electron configuration of a noble gas by becoming ions. Okay. If we take a look at a second example, this example is going to be aluminum and bromine. So aluminum is in group 3A, which means it has 3 valence electrons. It's going to react with bromine, which is in group 7A, and has 7 valence electrons. So we know that aluminum is going to want to give up all 3 of those valence electrons. The problem is, how many can bromine take? Only 1. So because of that, we are going to need 3 bromines. Okay. We could kind of draw it like this. Right, here's my second bromine. Oops. Okay, and here's my third bromine. Each of them has their 7 valence electrons. So what's going to happen here? 1 electron goes to this bromine. 1 electron goes to this bromine. 1 electron goes to this bromine. Right? As a result, I'm going to get aluminum with a +3 charge, and it's going to have the electron configuration of neon. And I get 3 bromides, each having 8 electrons around them and having a -1 charge, and so they've gotten the electron configuration of krypton. Okay, so sometimes that means that this compound would be written AlBr3 because I need 3 bromines to take those 3 electrons that aluminum has in its valence shell or its highest occupied energy level. So what we just wrote for aluminum and bromine is called a chemical formula. A chemical formula shows the number of atoms of each element in the smallest representative unit of a substance. So examples of chemical formulas are NaCl for sodium chloride, AlBr3 for aluminum bromide. Now, these ions in most ionic compounds are arranged in an orderly pattern. And that orderly pattern is going to have to do with the fact that we know that a positively charged ion isn't going to want to be next to another positively charged ion because we know that like charges repel. Same thing is true of a negatively charged ion. A negatively charged ion isn't going to want to be next to another negatively charged ion because like charges repel. So as a result, ionic compounds typically are arranged in a pretty orderly pattern. Because of this, ionic compounds do not exist as single, discrete, which just means kind of separate units, but as a collection of positively and negatively charged ions arranged in repeating patterns. And we're going to talk a little bit more about what that looks like. But again, the reason for this is because a positive ion is going to want to be next to a negative ion, which is going to want to be next to a positive ion, which is going to want to be next to a negative ion. That's more stable than positive ions being near each other and negative ions being near each other. Because of this, when we talk about ionic compounds, we talk about a formula unit, which I abbreviate FU, which is usually everyone's favorite abbreviation in class because you get to say FU to the teacher. Okay? So, for us, FU stands for formula unit, and the definition of the formula unit is that it is the lowest whole number ratio of ions in an ionic compound. So in a formula unit, you do not show the charges of the ions. A formula unit is electrically neutral. So for example, if I'm going to combine a magnesium ion, which has a +2 charge, and a chloride ion, which has a -1 charge, right? For those to combine so that I am electrically neutral, I'm going to need 2 chloride ions. Therefore, okay, the formula unit for magnesium chloride is MgCl2. Because overall I have to have a neutral charge, no charge. So I have +2, -1, -1, which gives me an overall charge of 0. So this is a formula unit. So you also could say that NaCl, besides being a chemical formula, is also a formula unit. Same thing would be true of AlBr3. So realistically, formula unit is the same as a chemical formula. It is just specific to an ionic compound. Okay, so a formula unit is that lowest whole number ratio of ions in an ionic compound. You typically don't show your charges in it, although I will never mark it wrong if your charges are in it. Formula units need to be electrically neutral. So what are some of the properties of ionic compounds? Most ionic compounds are crystalline, solids at room temperature, crystalline just means they typically have a crystal structure, and typically ionic compounds are going to be a solid at room temperature. This is again because the component ions are arranged in repeating three-dimensional patterns. For example, the sodium chloride that we talked about earlier. Each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions. So each ion is strongly attracted to each of its neighbors. And repulsions are minimized. So these large attractive forces result in a very stable structure. We know that these are stable because they have high melting points. So, to kind of help you picture what I'm talking about with these 6 sodium ions completely surrounded by 6 chloride, imagine that you are standing in the middle of a room and you are a sodium ion. In front of you would be a chloride. Behind you would be a chloride. To the left of you would be a chloride. To the right of you would be a chloride, right? That's 4 of the 6 chlorides that are surrounding you. There also, because these are 3-dimensional, there would be a chloride like above you standing on your head, and there would be a chloride ion underneath you that you would be standing on. So on every single side of a sodium ion, there's a chloride. Exactly the same thing is true for chloride. Chloride would have a sodium ion in front of it, a sodium ion behind it, a sodium ion to the left, a sodium ion to the right, a sodium ion above it, and a sodium ion below it. The result is you never end up with a sodium ion directly next to another sodium ion. That would cause a repulsion that would not be stable. So because these ions are also attracted to each other, we have a really large attractive force and we get a very stable structure. And we know that it's stable because most ionic compounds have a really high melting point. So this is from page 422 in your textbook. This is figure 15.8. And it talks about the beauty of crystalline solids such as these comes from their orderly arrangement of their component ions. So the reason that these ions all have different shapes has to do with how those ions are orientated around each other in space. And they kind of start doing that way down, remember, on that level where you can't even see individual atoms. But they keep doing that over and over again until it gets to the point where you actually can see it. And crystals and the studying of crystals is actually how chemists came to know and understand a lot about what's happening in ionic compounds. Because eventually they get big enough that you can actually physically see the shapes that these ions are orientating themselves in. So you don't have to know the names of crystals or anything like that. This is just to demonstrate to you that there are lots of different ways that these ions can arrange themselves around one another. The other thing we want to talk about with ionic compounds is their conductivity. Ionic compounds can conduct an electric current when they're melted or dissolved in water. The reason that this happens when they melt the structure breaks down and the ions move freely to positive and negative electrodes so that they can conduct an electric current. Because the ions are moving, it allows electric current to flow between the electrodes. When ionic compounds are dissolved, the ions are free to move and allow that current to flow. That is why during an electrical storm, you are supposed to steer clear of water. Water dissolves many ionic compounds, and there are lots of ionic compounds in the soil and the dirt and in the earth. So the water, typically the water on Earth, contains ionic compounds already dissolved in it, which means if electricity, like lightning, hits the water, there are ions that are free to move, and they will allow that current to flow through the water and potentially get you. So this is the reason why you steer clear of water during an electrical storm. Okay, is because of this conductivity of ionic compounds. Your homework is on page 429, questions 15, 17, and 18. Have a good day. Talk to you tomorrow.